Hello and welcome to Cruising Through Calculus. My name is Alex and today we're going to be looking at using the first derivative test, the second derivative test, and we're going to be checking for concavity. So let's jump right in. Our first problem says, find all points of relative minima and maxima using the first derivative test. So in order to use the first derivative test, we are going to find the derivative, and then we're going to figure out where it's equal to 0 and where it does not exist. A lot of students actually forget that second part and will only do the first part, but you have to do that in order to get the correct answers. So let's begin by finding the first derivative here. Looks like we're going to need to use the chain rule here. So we're going to take that 4/3 and bring it down. Keep the inside the same, subtract 1 from the exponent. I do have to multiply by the derivative of the inside, but that's just going to be 1, and multiplying by 1 isn't going to change anything. Over here, we're going to do the same thing. Bring down the exponent, leave the inside alone, subtract 1, multiply by the derivative of the inside, which again is 1, and then the derivative of a constant is 0. All right, now that we have our derivative, let's clean this up a little bit. So for example, I notice 3 here, 3 here, 3 here, 3 here, 4 will fit into 16 4 times. And then let's go ahead and write this out like this. We're going to have x minus 1 to the 1/3 over 4 plus, and then this 2 is going to be in the denominator, and we're going to take this piece and also move it to the denominator, like this. That will change it to a positive exponent there. Now at this point, what I'm going to do is I'm going to try to get a common denominator here. So the left side is going to need an x minus 1 to the 2/3, and the right side is going to need to multiply by 2 to get to 4. So this side needs an x minus 1 to the 2/3. This side needs an extra 2. So let's see what we're going to get here. Up here we have x minus 1 to the 2/3 times x minus 1 to the 1/3. Since the bases are the same, I can add the exponents. 2/3 plus 1/3 is just 1. So this is just going to be x minus 1 to the power of 1, or just x minus 1. Over here we're going to get 1 times 2, and we're adding here, so this is just going to be plus 2. In the denominator, we should now have a common denominator of 4 and then x minus 1 to the 2/3. Okay, up here, -1 plus 2 is positive 1. And I'd say that we've simplified this down. Now it's time to figure out where the first derivative is equal to 0 and where it does not exist. Well, setting it equal to 0 is actually really easy when it's set up like this. If you have a fraction like this and you're trying to figure out where it's equal to 0, just take the numerator and set it equal to 0. And I think you'll see very quickly that x has to be -1 to make the numerator 0. To figure out where the derivative does not exist, we actually take a look and see what makes the denominator equal to 0. And I hope you can see here, if you plug 1 in for x, that'll make the denominator 0, and therefore the derivative will not exist when x is equal to 1. Okay, this is perfect. These right here are the critical numbers. The critical numbers is where the derivative is equal to 0 and where the derivative does not exist. So what we do with these is we go and we draw a number line, and we put the critical numbers on that number line. So -1 and 1. Then what we do is we pick test numbers that are around these points, like 0, 2, -2. And what we do is we take these numbers and we plug them back into the first derivative, and we see if we get a positive answer or a negative answer. Now we don't care about this specific number. What we do care about is the positive or negative part, because anywhere where the first derivative is positive, that means the function is increasing. Anywhere where the first derivative is negative, that means the function is decreasing. So let's take a look here for a second. This is kind of important because this will help you when you're plugging these numbers in. If you look at the denominator, x minus 1 to the 2/3, I can rewrite the denominator here. In fact, just focus on the x minus 1 to the 2/3 part for a second here. That would be like the cubed root of x minus 1 and then squared, like this. So the reason why I'm focusing on this is because if you take anything that's right here, so any number that I plug in for x, and then I square it, I'm going to get a positive number. And then I'm going to take the cubed root of that, and the cubed root of a positive number is still a positive number. And then if you come back up here and we multiply that by 4, we're still going to get a positive number. So I guess what I'm trying to say is the denominator is always positive, which means all we have to do is worry about the numerator here. This is going to simplify this process a great deal. So take a look here. If we plug negative 2 in, just for the denominator here, we get negative 2 plus 1. Well, that's a negative answer. If I plug 0 in, 0 plus 1 is 1. That's positive. If I plug 2 in, 2 plus 1 is 3. That's positive. Here we go. We now have already figured out where the function is decreasing and where it's increasing. So we can use this to figure out where the local minima and maxima are. So to check it out here, if we have a negative, that means the function is decreasing. If we have a positive, that means it's increasing. Well, that must mean that that spot right here is a local minimum. Now, similarly, over here, if we have increasing and then increasing again, well, that's neither a local minimum nor a local maximum. So there's nothing going on right here, which means that there is only a local minimum in this problem here, and it happens when x is equal to negative 1. Now, if you read the question carefully, the question says to figure out what is the point of the local minimum, and points require an x and a y coordinate. We know the x coordinate is negative 1. So now what we have to do to find the y coordinate is take that and plug it back into here. All right, now I've already done that, and you don't get the nicest number in the world. In fact, you might even just want to use a calculator, because what I get is negative 0.417. And that is going to be our answer for the first problem. Our next question says, find all points of relative minima and maxima using the second derivative test. Okay, so to find the second derivative test, we are of course going to find the second derivative. But first we need to find the first derivative. So let's work on that here. Okay, we're going to need to use the quotient rule here. So we're going to need the derivative of the top multiplied by the bottom minus the derivative of the bottom multiplied by the top. And this is all going to be over the denominator squared, like that. Okay, so let's see if we can simplify this a little bit here. We're going to get negative 6x squared minus 12x plus 3x squared over our denominator here. And then we can simplify that a little bit further, because we're going to get negative 3x squared minus 12x over 3x plus 6 squared. Now, before we actually find the second derivative, part of the second derivative test is that we need to know where the first derivative is equal to 0. So that means we need to take the numerator here and set it equal to 0 and see what we get. So let's do that. Now, if I'm going to do that, let me go ahead and factor out a negative 3 and an x. A negative 3 and an x. So what do we get when we do that? Looks like we get x plus 4. All right, now I can see that the derivative is equal to 0 when x is equal to 0 and when x is equal to negative 4. Okay, this is good. Now it's time to find the second derivative. So to find the second derivative, that means finding the derivative of the derivative. So we're going to need the derivative of this here. And actually, I think that this is going to take up a bit of room. So let me go ahead and just kind of erase things here, move things around, and then we'll continue. All right, I put our first derivative up here. I put where the first derivative is equal to 0. It's now time to find the second derivative. All right, that means we're going to need to use the quotient rule again. So let's find the derivative of the top multiplied by the bottom minus the derivative of the bottom, which we're going to need to use the chain rule on here, times the top, all over the denominator squared. And notice it was already squared before, so if you square a square, you get to the fourth. All right, so here's what we're going to do now. We're going to try to factor things out here a little bit in a way that hopefully will clean this up. And I think you'll see it actually does clean up decently well, or at least well enough for us to use the second derivative test pretty easily. For example, take a look here. We can factor a negative 6 out from here, leaving us with an x plus 2. This part has to remain the same. Over here, I'm actually going to multiply these all out. So like 3 times 2 is 6, and then I'm going to distribute the 6 here. So 6 times 3 will give us 18x plus 36. 18x plus 36. And then over here, we can take a negative 3 and an x out, leaving us with an x plus 4. This is still all over our denominator, 3x plus 6 to the fourth. All right. This doesn't look very good at first, but check it out. In order to use the second derivative test, we need to plug in 0 and -4 in to the second derivative, and we need to see if we get either a positive answer or a negative answer. Now, believe it or not, this isn't going to be as bad as it looks like. Let me explain. Let's go ahead and start by plugging 0 in to the second derivative. Okay, well, for starters, notice in the denominator, this is to the fourth power. That's always positive, so I'm not going to even worry about that. Then, check this out. This is kind of interesting. Over here on this side, we have a negative 3x times x plus 1, and then, or x plus 4, and then this piece is multiplied by this piece here. Well, if I do take 0 and plug it in right here, this is going to be 0. 0 times that is 0, and then this, which is 0, times this piece here, means that this entire piece over here is going to be equal to 0. So I don't have to worry about that either. Here's another thing I don't have to worry about. 3x plus 6 squared. That's always positive. So all I have to worry about is this little piece right here, negative 6x plus 2. So if I take 0 and plug it in here, I'm going to get a negative answer. Can you believe how crazy this looks at first and yet how nice that ended up? All right, next let's plug -4 in. And believe it or not, the same thing is going to happen, because take a look all the way over here. We have an x plus 4. If I take -4 and plug it in over here, this entire piece is 0. This is still positive, that's still positive, so I just need to worry about this here. Okay, so if I plug -4 in, that's going to be -2 times -6, so we're going to get a positive answer. Okay, the second derivative test says that if you find where the first derivative is equal to 0, and then you take these numbers and plug it into the second derivative, if you get a negative answer, that's going to be a local maximum, not minimum. And if you plug it in and get a positive answer, that's going to be a local minimum. One way to try and remember why having a negative answer gives you a local maximum and a positive answer gives you a local minimum is to think about concavity. If the second derivative is negative, that means it is concave down. And if the second derivative is positive, that means it's concave up. And just informally speaking, can you see how a concave down is going to give you a maximum and a concave up is going to give you a minimum? That's how you can remember this. All right, so we now have almost everything we need to answer this question here. We know that the local maximum occurs when x is equal to 0. And we know that the local minimum occurs when x is equal to -4. The only thing left to do is to find the y-coordinate here. So we need to take these numbers and plug it back up into our original function. Now 0 is pretty easy. If you plug 0 in, you're just going to get 0 divided by 6, which is 0. -4, though, is a little bit more complicated, but not too bad. I've actually already done this ahead of time here. And what I got is 8/3. So that's what that's going to turn into 16 up here, and then we're going to get -12 plus 6. Yeah, you do get 8/3. I just did a quick mental check here. And so those are the answers to this question. Our next problem says, find all points of absolute minima and maxima on the given interval. Now, I think a lot of people mistakenly think that perhaps you need to use the first derivative test in order to find the absolute minima and maxima. But that's not true, because the first derivative test will only give you the local minima or maxima. So in order to find the absolute minima or maxima, we are still going to use the first derivative, but not the first derivative test. So we won't need to draw a number line, for example, and figure out increasing and decreasing. Another thing to note is that if they ask for absolute minima or maxima, they're always going to give you an interval. This is going to be part of our method of finding the absolute minimum and maximum. Nonetheless, we do start off the same way, which is finding the derivative and figuring out where it's equal to 0 and where it does not exist. In other words, we're going to find the critical numbers here. So let's start by finding the derivative. We're going to start off with the chain rule here, bring down the 7/3, subtract 1 from the exponent, leave the inside alone. I would multiply by the derivative of the inside, but that's just 1, so why bother doing that? Same thing over here, bring down the exponent, subtract 1, leave the inside alone, multiply by the derivative of the inside. Over here we have the derivative of a constant, so we don't even have to worry about that. All right, so let's see what we got here. Usually a lot of the work on these is just the cleanup parts. Okay, so this is what we have so far. What I'd like to do now is get a common denominator. So this side over here is going to need a 2 over 2 to turn that into 18. And then this side over here is going to need an x plus 1 to the 2/3 on the numerator and denominator. So let's see what happens when we do that. Okay, well, let's see here. We still have the 7. Now we have x plus 1 to the 4/3 multiplied by x plus 1 to the 2/3. Well, since x plus 1 and x plus 1 have the same base, I just need to add the exponents. 2/3 plus 4/3 is 6/3, and 6/3 is just squared. Over here we have 14 times 2, which is 28. And in the denominator, we should have 18x plus 1 to the 2/3, like this. All right, this is looking pretty good here. Now, what do we need to do next? We need to figure out where it's equal to 0 and where it does not exist. Well, okay, where it's equal to 0 is going to be where the numerator is equal to 0, and where it does not exist is where the denominator is going to be equal to 0. So let's take a look at that. To find out what makes the derivative equal to 0, we need only take the numerator and set it equal to 0. So what are we going to do here? We're going to add 28 to both sides. We're going to divide both sides by 7. That's going to give us 4. Then we're going to take the square root of both sides. So that's going to give us plus or minus 2. And then we're going to subtract 1 from both sides to get plus or minus 2 minus 1. So that means we're going to have 2 minus 1 and negative 2 minus 1 as our answers. So we're going to get 1 and negative 3. Now that's where the numerator is equal to 0. To figure out what makes the denominator equal to 0, I hope you can see pretty quickly, that's going to be when x is equal to negative 1. So that means these are our critical numbers here. Now, here's something we have to do. We have to see if our numbers are actually part of our interval or not. So for instance, 1 is outside of our interval, so we can ignore that. Negative 3 is part of our interval, so that's okay, and so is negative 1. So that means we can proceed to the next part. The next part is we're going to take the numbers that we just found and we're going to actually plug them back into the original equation. What we're looking for are the largest and smallest values, because whatever those are going to be our absolute maxima or minima. Now, let's see here. There are 3 numbers that we have to test. First, we have to test our critical numbers, which is negative 1 and negative 3. Then we also have to test the end points of our interval. So that would be negative 3, which we already have here, and then 0, which we don't have, so we need to include that. All right, now, I've already done this ahead of time. I plugged these values into a calculator. Although I don't think we necessarily need to for all of them. For example, take a look at negative 1 here. If we take negative 1 and plug it in here, this is going to be 0, and this is going to be 0, and you're going to be left with negative 2. Negative 3, though, not nearly as nice. So when I plugged negative 3 into a calculator, I got 3.04. 0 is also not going to be the worst number to plug in. In fact, what we would end up with is 1/6 minus 14/3 and then minus 2, which turns out to give us negative 13 over 2, which is the same thing as negative 6.5. Now that we've done this, what we need to do is find the largest number and the smallest number. So I hope you can see here that the largest number is going to be 3.04. The smallest number, or maybe the most negative, if you will, is going to be this negative 6.5 number here. So in other words, we have everything that we need in order to answer this question. We know that the absolute maximum occurs when x is equal to negative 3, and we know what that number is because we already plugged it back into our original function. Similarly, our absolute minimum happens when x is equal to 0, and since we already plugged that back in, we got negative 6.5. And so those are our answers. Our next problem says, find the open intervals where the function is concave up and concave down. Now, this is not the second derivative test we're going to be doing here, because the second derivative test is where you take the first derivative, find out where it's equal to 0, and plug that into the second derivative. That doesn't mean we're not going to be using the second derivative, though, because using the second derivative can help us find concavity. And the process is very similar to the first derivative test. What we're going to do is we're going to find the second derivative, figure out where it's equal to 0 and where it does not exist. Then we're going to draw a number line, pick some test numbers, and see where we get positive or negative answers. That will tell us where we get concave up and concave down. So let's start by finding the derivative. Here we're going to need to use the chain rule. So bring the 2 down, subtract 1 from the exponent, leave the inside alone. We're going to have to multiply by the derivative of the inside, so that means we're going to need to use the quotient rule now. So that means I need the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. Now, because we got 1 and 1 here, and these were relatively simple functions that we were finding the derivative of, this actually cleans up pretty nicely here. In fact, what we get is 8x minus 8 over x plus 3 cubed. So the x plus 3 cubed came from the x plus 3 times the x plus 3 squared, and then all I did was I distributed everything up here in combined like terms, and I got 8x minus 8 here. All right, time to find the second derivative. We're going to need to use the quotient rule. So we're going to need the derivative of the top times the bottom minus the derivative of the bottom, so we're going to need to use the chain rule, times the top, all over the denominator squared. Now, it was already cubed to begin with, so if you cube and then square it, you're going to get to the power of 6 here. All right, now what we're going to do is we're going to try to figure out what makes the numerator equal to 0. And actually, I think if we take a moment to look at the numerator and simplify it, this will simplify down pretty nicely here. So let me explain what I mean. I want you to notice that there is an x plus 3 right here, and there's also an x plus 3 over here too. Ooh, that should be x plus 3. There we go. I want you to also notice that there's an 8 over here, and there's actually an 8 here and here. So here's what we're going to do. We're going to take this x plus 3 and this x plus 3, and we're going to factor out an x plus 3 squared. And then we're also going to take this 8 and then these 8s and factor them out as well. So let me do this. Let me go ahead and erase some of our work up here, and let me move this up here, and then we'll continue. All right, I took our first derivative and put it up here. I've put what we found so far of our second derivative. Now what we're going to do is we're going to be factoring out this x plus 3 and this x plus 3 and this 8 and also this 8 over here. Let's see what we're going to get here. So if I take an 8 and I'm going to take an x plus 3 squared out, because that's the GCF of these two here, what are we going to be left with? Well, on this first part, I already took the 8, and then I took 2 of these, leaving me with just 1 of them. Let's see here, that 3 is still there. And then I took an 8 out from here. So that's going to leave me with just x minus 1. I didn't do anything in the denominator, so that's stayed the same. Okay, so, hey, check this out. X plus 3 squared, x plus 3 to the 6th. This will cancel with this, leaving us with 4 of these. And then, even better, if I distribute this negative 3 here, I'm going to get a negative 3x and a plus 3, which I can combine with this x plus 3 over here. So I'm going to end up with an 8. 3 plus 3 is 6. X minus 3x is negative 2x, all over x plus 3 to the power of 4. And I can even take a 2 out, which I guess I could have done earlier, but I'm just now seeing this, giving me 3 minus x over x plus 3 to the 4th power. Whew. Okay, so the second derivative actually simplified down pretty nicely. Now we need to figure out where it's equal to 0 and where it does not exist. And I hope you can see what that is pretty quickly here. It's equal to 0 where the numerator is equal to 0 when x is equal to 3. It does not exist when the denominator is equal to negative 3, because that'll give us division by 0. So now what we're going to do is we're going to take these two numbers here, put them on a number line. Then we're going to pick some test numbers around them, plug these back into the second derivative down here, and we're going to see what we get. Now, this is nice. X plus 3 to the 4th is always positive. So is 16. So the only thing I have to worry about is this 3 minus x here. So check it out. If I do 3 minus negative 4, that will give me positive. If I plug 0 in, that'll be just 16 times 3, which is definitely positive. And then if I take 4 in, 3 minus 4 is negative 1. That'll give me a negative answer right there. Okay, this is great. Now we can figure out where it's concave up and concave down just by looking at our chart over here. It's going to be concave up wherever it's positive. So that will be negative infinity to negative 3. And then from negative 3 to 3, it's going to be concave down from 3 to infinity. Now, one last thing I'd like to point out is that even though this question doesn't ask for it, there is a point of inflection. So the x-coordinate for the point of inflection is where it changes, in this case, from positive to negative concavity. So that's when x is equal to 3. If I wanted to find the y-coordinate, I would plug it back up into here and see what I would get. So 3 minus 1 is 2. So we get 2 over 6. 2 over 6 is just 1/3, and then 1/3 squared is 1/9. So this would be our point of inflection here. Now, like I said, our question doesn't ask that, so I didn't need to do that, but I just wanted to include that just in case it's helpful. There's quite a bit going on with these problems, which is why I chose one of each type of question. Our first question was a first derivative test question. Our second question was an absolute maximum or minimum question. Then we did the second derivative test, and then we figured out what concavity was. Now, be sure that you're clear on what each of these are. For example, the first and second derivative test both do the same thing. They both find local minimum or maximums. However, you do not use the second derivative test for concavity. That doesn't mean you don't use the second derivative. In fact, you do use the second derivative. You figure out where the second derivative, is either positive or negative, and that will tell you if you have concave up or concave down. But that's different than the second derivative test, because the second derivative test is where you figure out where the first derivative is equal to 0, take those numbers, plug them into the second derivative, and see if you get positive or negative answers. Finally, let's talk about absolute minimum and maximum. You don't use the first derivative test or the second derivative test or concavity. What you do is kind of a little bit of the first derivative, and then you also have to test the endpoints as well. That's an important part of that one. If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.